Okay, good evening and welcome everyone. Today I went through problem 15 in section 1.4, and it was a difficult problem. I mean, definitely I would not put something this difficult on an assessment, but I would do something like this that required the same techniques in order to solve it. So it was, and I think it started with just this. In the numerator, 1 over x plus delta x minus 1 over x, all of that over delta x. And it's the limit as delta x approaches 0 from the negative side. And so that is a little bit of a different concept, but just keep in mind that this x and this delta x are not the same thing. You can treat delta x like a number, even though most likely in calculus it'll be an interval of x values, the change in x. And we'll see that a lot more when we define the derivative. But for now, just say, okay, x is some variable and delta x is some variable or some range of variables, and they're not the same thing. So in general, when you do this kind of a problem, you want to get rid of the denominator, simplify that, or at least this denominator, and we'll worry about this denominator later. Right now, if you substitute in 0 for delta x, you're dividing by 0, which, as we know, is problematic. So, as we showed at the start of the recording, if we go delta x over 1, it's a little bit easier, and then we can say, oh, we can multiply by the reciprocal, multiply both numerator and denominator by 1 over delta x, and life will be good, because that will eliminate this one denominator. So we can just go like this. Pause the recording if you need to. All right. Next, we have the limit as delta x approaches 0 from the negative side of, notice this is all 1. So it's still there, but it's really dividing by 1. Now we have this numerator multiplied by 1 over delta x right here. Okay, so far so good. I'm going to continue on down. So now the philosophy here, I guess I went a little bit too early, is what can we do to get right here a common denominator? And the easy answer would be to multiply everything here times x over x, multiply everything here times x plus delta x over x plus delta x, which is what we did right down here. So this is just 1, the multiplicative identity, and this is just 1, the multiplicative identity. Just a little makeover that will give us common denominators. When you're in kindergarten, you thought, oh, I'll never have to do common denominators again, but here you are at another version of kindergarten. So when you multiply this out, you wind up with x times 1 is x, and you wind up, and really, you don't need to multiply these through and simplify. I can just say x times the quantity, x plus delta x. And over here, x plus delta x times 1, x times the quantity, x plus delta x. And now you'll notice that the denominators here are common. My 1 over delta x from way back, I just kept. And again, you don't have to do anything with it. You can, but you don't have to. Okay, I'm going to hold still for a second, let everyone process that for a moment. Notice down here we've got a minus the quantity. Because you multiplied a quantity, we'll have to distribute that, because these guys are a great place for people to lose a negative sign. Okay, so now we have the limit as delta x approaches 0 from the negative side, it's late, of I took the 2, this fraction minus this fraction, and now I have a common denominator, so I can combine the numerators. And notice I distributed this negative sign over to the delta x. So I have x minus delta x, minus, not plus, over the common denominator, x times the quantity, x plus delta x. All of that times 1 over delta x. This guy is still here. So it's looking a little better. Okay. next up, I can simplify by saying, well, x minus x is just 0. So I have 0 minus delta x over x times the quantity x plus delta x. Getting a little better. Ooh, I see something nice here. Notice what's going to happen with this delta x and this delta x. You're right. I'm going to get rid of the shade because we're almost done. Now we have negative 1. Notice they don't cancel. They divide out to become negative 1 over x times the quantity x plus delta x. Notice this right here and this right here, these divided it out. So this is really just negative 1 times 1 is just negative 1. So that's where this went away to. So now we have negative 1 over that common denominator, x times x plus delta x, which is negative 1. Now we can say, let x be 0 here, really. I can say negative 1, or delta x rather, negative 1 over x times the quantity x plus 0. So that's going to be just x times x is x squared. And you're not used to this. You're used to limits being integers, but in this case, it is negative 1 over x squared, and that is a legitimate limit. And I think that's what caused problems for some of you. Okay? So pause this as needed. I'm going to pause and get number 25 set up, so you won't notice it. Okay, we're back. So I took a moment and paused and did a little graph here for this greatest integer function. In this, our author, bless their heart, greatest integer function, uses a little different notation for this one. Greatest integer function. Last year we had slightly different notation, and I hope I'm not mixing them up. Sometimes I do. But for the greatest integer function, you go and you come on, brain. Stand by. I'm going to pause this again. Okay, I'm back. I didn't quite have myself together there, but I think I do now. So when we did college algebra, the greatest integer function was denoted like this. Oh, other way. Was denoted like this. Here in calculus, it's denoted with like a double whammy. And so those mathematicians sometimes can't make up their mind. And so greatest integer function, recall, is less than or equal to n. So we think about that, and I'll give you some examples here. So if you just have an x, and in our case, let's do 2.1, 2.9, 3, and 3.1. I think that'll give us a sense of what we're working with, because we have our limit as x approaches 3. I think this will give us a sense. Okay, so then if we just do, the next column would be the greatest integer of x. 2 then, less than or equal to 2 is 2. 2.1 less than, in this case, is also 2. 2.9, broken record, 2. How about 3? Well, now we bump up to the next increment. It's 3. And then this one is also 3 at 3.1. Okay, so notice in our function we have the greatest integer of the absolute, or not the absolute, the greatest integer of the opposite of x. So then let's make a column for that, and we'll slowly build up to 2 minus. Okay, now this one's a little trickier, so put on your thinking caps, everyone. Less than or equal to -2, because keep in mind, we're using x's from this column, putting in here, take the opposite, take the greatest integer. Well, that would still be -2. Now we put in 2.1 for x, take the opposite. Now we have to go less than this time. Less than. Well, what's the next integer that is less than 2.1? Well, it's -3. Keep in mind, -3 is less than -2. So 2.9 then would also be -3. So here's where we have to be careful. We get to 3, negative, and we're at an equal to. So that's also -3. And then at 3.1, the opposite of 3.1 is -3.1. What's the nearest integer less than 3.1? Well, now we go to -4. Okay, we're almost ready. Hang in there. I know this is kind of a tough one. 2 minus the greatest integer of the opposite of x. So now we go 2 minus -2. I'm going to do this one longhand. 2 minus -2 equals 4. Okay. 2 minus -3 equals 5. So this one will also be 5. This one will also be 5. Now we go 2 at 3.1. We go 2 minus -4, and we go to 6. Okay? So that's where you wind up with this graph up here. I left the open circles and closed circles off on purpose. So now we're going to go, notice at 2.1 through 2.9. So in this area here, I'm at 5. Okay? And at 3, I'm also at 5. So that means that's a closed circle there, an open circle there, closed circle there, open circle there, and at 1, closed circle, open circle. And that means up here at 3, my value is 5. Right here, closed circle. So then I have an open circle there, I don't occupy, and jumps up to 6. Okay, so here's the thing, right up here. Here's the function, the limit as x approaches 3 from the negative side. Okay, is right there. So let's check it out. So the limit as x approaches 3 of 2 minus, let's say from the negative side, 2 minus the opposite of x, greatest integer function. It's kind of a lame 2. Okay, again, so we're approaching 3. Right here, we're between 2 and 3. Approaching 3, approaching 3. We're at 5, baby, the whole way. Even as we get really, really close to 3, we're still at 5. So that equals 5. Okay? Let's go and clash the limit as x approaches 3 from the positive side of 2 minus the opposite of x, greatest integer function, equals, okay, so now we're at 3 from the positive side, so we're up here. Notice we're between 3 and 4. We're getting closer and closer and closer and closer to 3. Very, very close to 3. We're still at 6 is my limit. Equals 6. Okay? So now the big message is, as we approach 3 from the negative side, my limit is 5. As we approach 3 from the positive side, my limit is 6. So what does that mean? That the limit, maybe I should use yet another color, the limit as x approaches 3 of 2 minus greatest integer of the opposite of x. Since negative side 5, positive side 6, that means they do not agree, so the limit does not exist. Whew, I'm exhausted. We're 15 minutes into it. That's probably enough for you to listen. I hope that this is helpful. If not, please ask me questions tomorrow in class. Have a good night, everyone. Bye.